could close your eyes for a moment and imagine something with me. Imagine that humanity has finally done it. After centuries of dreaming, after thousands of science fiction novels and movies, after generations of physicists working day and night, we have finally built a functioning warp drive. The ship is ready. The crew is inside. The destination is set. A beautiful Earth-like planet orbiting a star just 12 light-years away. A new home for humanity. The captain gives the order. The warp bubble forms around the ship. Space itself begins to bend and fold. The stars outside stretch into lines of light and then disappear entirely. Inside the ship, everything feels perfectly normal. No shaking. No acceleration pushing anyone into their seats. Just calm, quiet, smooth travel. The journey that would have taken thousands of years with conventional rockets is going to take just a few days. Everyone on board is excited. Everyone on Earth is watching. This is the greatest moment in human history. And then they arrive. But something is wrong. Something is catastrophically, horrifyingly wrong. The planet they were traveling to, that beautiful blue and green world with oceans and continents, and perhaps even life, is gone. Not gone as in it disappeared, gone as in it has been sterilized. Its atmosphere has been stripped away, its oceans have been boiled into nothing. Its surface has been scorched to bare rock. Everything that once lived there, everything that could have been a new beginning for humanity, has been completely and utterly destroyed. And here is the part that will keep you awake tonight. The ship did this. Not with weapons, not with any intention of harm. The simple act of arriving, the simple act of the warp bubble stopping, released so much energy in the forward direction that it was equivalent to billions upon billions of nuclear weapons, all detonating at once, focused like a laser beam directly at the destination. The very technology that was supposed to carry humanity to the stars turned out to be the most devastating weapon ever conceived. Not designed as a weapon, not intended as a weapon, but a weapon nonetheless, built into the fundamental physics of how warp travel works. This is not science fiction. This is not speculation. This is what the mathematics tells us. This is what peer-reviewed research published by physicists at the University of Sydney demonstrated in 2012. And today, we are going to go deep into this. We are going to understand exactly why this happens, how it works, what the physics actually says, and whether there is any possible way around it. We are going to start from the very beginning, from Einstein himself, and build our way up to one of the most terrifying conclusions in all of theoretical physics. Before we dive in, if you are someone who is fascinated by the universe, if you are someone who wants to understand reality at its deepest level, if you are someone who believes that knowledge is the greatest adventure a human mind can go on, then this channel is for you. Hit that subscribe button right now. Press that like button. And in the comments below, tell me this. If you could travel anywhere in the universe instantly, but you knew that your arrival would destroy everything at your destination, would you still go? Think about that as we go through this video. Your answer might change by the end. Now, let me take you back to the research that changed everything we thought we knew about warp travel. In March of 2012, a team at the University of Sydney, part of the School of Physics, published a paper that sent shockwaves through the theoretical physics community. The team consisted of Brendan McMonigal, Geraint Lewis, and Philip O'Byrne. The paper was titled The Alcubierre Warp Drive on the Matter of Matter. It was submitted to the RCIV preprint server with the reference number 1202-5708 in the General Relativity and Quantum Cosmology section. Now, what makes this paper so special is not just what it found, but how it approached the question. You see, for nearly 2 decades before this paper, ever since Mexican physicist Miguel Alcubierre first proposed his warp drive metric in 1994, almost all of the scientific discussion had focused on one single problem: the energy requirements. Everyone was asking, how much exotic matter do we need? How much negative energy is required? Can we reduce the amount? Can we find alternative configurations? These were important questions, and we will discuss them today. But the Sydney team asked a completely different question. A question that, looking back, seems so obvious that it is almost embarrassing that nobody had rigorously addressed it before. Their question was simple. What happens to the stuff that is already out there in space? The particles, the atoms, the photons, the cosmic microwave background radiation. What happens to all of that when a warp bubble passes through it? Think about it. Space is not empty. I know we call it the vacuum of space, and yes, compared to the air you are breathing right now, space is incredibly empty. But it is not truly nothing. There are roughly 1 to 2 hydrogen atoms per cubic centimeter in interstellar space. There are photons everywhere, leftover radiation from the Big Bang filling every cubic centimeter of the universe. There are cosmic rays zipping through space at nearly the speed of light. There are dust particles, stray electrons, neutrinos. Space is a very thin soup, but it is not nothing. So what happens when you drive a warp bubble through this thin soup at faster than light speeds? The Sydney team set up numerical simulations to find out. They modeled a warp bubble moving through a field of particles and traced what happened to those particles as the bubble encountered them. And what they found was devastating. The particles do not simply pass through the bubble. They do not get pushed aside like water around a boat. Instead, they get swept up by the front wall of the warp bubble and trapped there. The extreme curvature of space-time at the bubble's leading edge captures these particles and holds them. As the bubble continues to move, it accumulates more and more particles. Like a snowplow driving through fresh snow, the front face of the warp bubble gathers everything in its path. But unlike snow on a plow, these particles do not just sit there passively. They get energized. They get blue-shifted to extraordinary energies by the extreme space-time geometry of the bubble wall. The longer the trip, the more particles accumulate. The faster the bubble moves, the more energy each trapped particle gains. And then, when the bubble stops, when the warp drive is turned off and the ship arrives at its destination, all of those accumulated hyper-energized particles are released, forward in a concentrated beam. At the destination, the energy involved is not trivial. For a trip of just a few light years at superluminal speeds, the energy released upon arrival would be comparable to a gamma-ray burst, one of the most energetic events in the known universe. Enough to sterilize a planet, enough to strip an atmosphere, enough to end any and all life at the destination before the crew even has time to look out the window. This is the story we are going to explore today. But to truly understand it, we need to start at the very beginning. We need to understand why faster-than-light travel is so difficult in the first place. We need to understand what a warp drive actually is. And then we need to understand, in precise physical detail, why it carries this terrible, possibly unavoidable cost. Let us begin with the speed of light itself. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would completely revolutionize physics. His name, as you probably know, was Albert Einstein. One of those papers introduced the special theory of relativity, and within it was buried perhaps the most famous equation in all of science: E equals mc squared. But the deeper implication of special relativity was something even more profound than that equation. It was the establishment of an absolute cosmic speed limit. The speed of light in a vacuum is exactly 299,792,458 meters per second. We usually round this to about 300,000 kilometers per second, or about 186,000 miles per second. In physics, we simply call it c. And what Einstein showed was not just that light happens to travel at this speed, but that this speed represents a fundamental limit on how fast anything in the universe can move through space. Now, why? Why should there be a speed limit at all? Think about your everyday experience. If you are in a car going 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, an observer on the roadside sees the ball going 150 kilometers per hour. Speeds add up, simple, intuitive, and wrong. At least, wrong when you get close to the speed of light. Einstein showed that as an object with mass moves faster and faster, something strange happens. It takes more and more energy to accelerate it even a tiny bit more. Not linearly more, exponentially more. As you approach the speed of light, the energy required to accelerate you further approaches infinity. You would need literally infinite energy to accelerate any object with mass to exactly the speed of light. And since infinite energy does not exist, no object with mass can ever reach light speed. It is not a technological limitation. It is not something we can engineer our way around with better engines. It is built into the very fabric of how space and time work. But it gets even stranger than that. As you move faster, time itself slows down for you relative to a stationary observer. This is called time dilation. At 90% of light speed, your clock runs at about 44% the rate of a stationary clock. At 99% of light speed, your clock runs at about 1/7 the rate. At 99.99% of light speed, your clock is ticking at less than 1% of the normal rate. Time literally stretches out. Simultaneously, space itself contracts in your direction of travel. This is called length contraction. The faster you go, the more the distance in front of you appears to compress. These are not illusions. They are not perceptual tricks. They are real, measurable, physical effects that have been confirmed by countless experiments. GPS satellites have to correct for time dilation, or they would give you wrong positions. Particles called muons created in the upper atmosphere by cosmic rays should decay before reaching the ground based on their normal lifetime. But because they are moving so fast, time dilation allows them to survive long enough to reach our detectors on the surface. This is reality. Now, what does this mean for space travel? It means that the universe is, in a very real sense, frustratingly large relative to our ability to cross it. The nearest star system to our Sun is Alpha Centauri, at about 4.24 light-years away. That means light itself, the fastest thing possible, takes 4.24 years to get there. If we could build a ship that travels at 10% the speed of light, which is already wildly beyond our current capabilities, the trip would take about 42 years. At 1% the speed of light, it would take 424 years. And Alpha Centauri is our closest neighbor. The galaxy is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The observable universe is 93 billion light-years in diameter. With conventional travel, even at significant fractions of light speed, the universe is simply too big. It would take hundreds of thousands of years to cross our own galaxy, millions of years to reach the next one. The stars would be born, live, and die while we are in transit. Civilizations could rise and fall on Earth before our ship arrives anywhere interesting. This is the tyranny of the speed of light. And it is why, ever since Einstein revealed this limit, physicists and dreamers alike have been searching for a loophole. And here is where it gets truly interesting. Because there is a loophole. Not in the speed of light itself, but in what the speed of light actually restricts. Einstein said that nothing can travel through space faster than light. The key words there are through space. He placed a speed limit on objects moving through the fabric of space-time. But here is the thing. What about the fabric itself? What if space itself could move? Is there a speed limit on how fast space can expand or contract? The answer is no. There is not. We know this because we can observe it happening right now in our own universe. The universe is expanding. Galaxies are moving away from each other. And the further away a galaxy is, the faster it appears to be receding from us. There is a distance called the Hubble radius, beyond which galaxies are receding from us at speeds greater than the speed of light. They are not violating Einstein's rules, because they are not moving through space faster than light. The space between us and them is expanding so fast that the total recession speed exceeds c. Those galaxies are being carried along by expanding space, like dots on a balloon that is being inflated. And in the very early universe, during a period called cosmic inflation, space expanded at rates wildly faster than light. The entire observable universe went from something smaller than an atom to something larger than a grapefruit, in a fraction of a trillionth of a trillionth of a trillionth of a second. That expansion was space itself stretching, and it had no speed limit. So here is the loophole that a brilliant Mexican physicist noticed in 1994. If space itself has no speed limit, what if you could somehow contract space in front of you and expand space behind you, creating a wave of space that carries you along with it? You would not be moving through space at all. You would be stationary within your own little pocket of flat space. But that pocket would be riding a wave of spatial distortion that can, in principle, move faster than light. You would arrive at your destination before light from your origin would, but you personally never exceeded the speed of light. You never even moved. This is the Alcubierre warp drive. And it changed everything. Miguel Alcubierre was born in Mexico City in 1964. He earned his PhD in physics from Cardiff University in Wales, studying general relativity and numerical solutions to Einstein's field equations. By all accounts, the inspiration for his most famous work was surprisingly casual. He was watching Star Trek, and he thought to himself, is there anything in Einstein's equations that would actually allow this? Not as fantasy, not as fiction, but as real, legitimate physics. So he sat down and worked backwards. Instead of starting with a physical mechanism and deriving the space-time geometry it would produce, he started with the space-time geometry he wanted, a bubble of flat space moving faster than light, and asked what distribution of matter and energy would be required to produce that geometry according to Einstein's field equations. In 1994, he published his paper in the journal Classical and Quantum Gravity. The paper was titled The Warp Drive, Hyper-Fast Travel Within General Relativity. And in it, he presented a completely valid solution to Einstein's field equations that described effective faster-than-light travel without actually violating any of the principles of general relativity. Let me explain how this works in detail, because the mechanics are beautiful and understanding them is crucial to understanding why the destruction problem exists. Imagine empty space as a flat sheet of rubber. Now, imagine that you can pinch and stretch this rubber in specific ways. In front of a certain point, you contract the rubber, pulling it together, making the distances smaller. Behind that point, you stretch the rubber, pushing it apart, making the distances larger. If you do this continuously, the point between the contraction and expansion effectively moves forward, carried by the wave of spatial distortion. Now, make this three-dimensional. You have a ship. Around it, you create a bubble of completely flat, undistorted space-time. This is the warp bubble interior. The ship sits in this flat region, and feels absolutely nothing unusual. No acceleration, no forces, no time dilation relative to someone else inside the bubble. It is, from the ship's perspective, as if they are just floating in normal space. But at the boundary of this bubble, at the bubble wall, space-time is extremely distorted. In front of the bubble, space is being violently contracted. Behind the bubble, space is being violently expanded. This creates a ripple in space-time itself, and that ripple can propagate at any speed, including faster than light, because it is space that is moving, not anything moving through space. The mathematical description of this is what we call the Alcubierre metric. It is a specific solution to the Einstein field equations, which are the fundamental equations of general relativity that describe how matter and energy curve spacetime. The metric describes the geometry of spacetime around the warp bubble, including the flat interior, the distorted walls, and the normal space outside. One of the most remarkable properties of this solution is what happens to time inside versus outside the bubble. In most discussions of relativistic travel, there is always a twin paradox issue. If you travel near the speed of light and come back, less time has passed for you than for people who stayed home. But in the Alcubierre metric, there is no such time dilation for the people inside the bubble. Their time runs at the same rate as time for a distant stationary observer. If you travel to a star 10 light-years away at warp speed and the trip takes you 1 day, then 1 day has also passed back on Earth. There is no twin paradox. This is because the space inside the bubble is flat. The travelers are not experiencing any relativistic effects whatsoever. All the exotic physics is happening at the bubble wall, not inside. Another remarkable property is the absence of acceleration. In conventional travel, to go faster, you need to accelerate. This pushes you back in your seat. At high accelerations, it can crush you. To reach anything close to light speed in a reasonable time frame, you would need accelerations that would turn a human body into paste. But in a warp drive, there is zero acceleration. The ship never speeds up. The ship never slows down. The ship is always stationary relative to the space immediately around it. It is the space that is doing all the moving. You could stand on the bridge of a warp-driven ship holding a cup of tea, and the tea would not even ripple. This is why the Alcubierre drive captured the imagination of physicists and science fiction fans alike. It seemed to solve every problem at once. Faster than light speed, no time dilation, no acceleration forces, no relativistic mass increase. It was perfect. Except, it was not perfect. It had problems. Serious problems. And we need to understand those problems in order to understand why the destruction issue is so devastating. The first and most immediately obvious problem was the energy requirement. When Alcubierre calculated what kind of matter and energy would be needed to create his warp bubble according to Einstein's field equations, the answer was deeply troubling. You would need something called exotic matter. Specifically, you would need matter with negative energy density. Now, what does negative energy density mean? In normal physics, all matter and energy we interact with in daily life has positive energy density. A rock has positive energy. A photon of light has positive energy. Even empty space, as far as we can measure, has either zero or a very small positive energy density. Negative energy density means something that has less energy than empty space. Less than nothing in a sense. This might sound impossible, but it actually is not entirely. There is a well-known quantum mechanical effect called the Casimir effect that demonstrates negative energy density can exist. If you place two perfectly flat, uncharged metallic plates extremely close together in a vacuum, the quantum fluctuations between the plates are restricted compared to those outside the plates, and this creates a region between the plates with negative energy density relative to the surrounding space. The plates actually attract each other because of this. This has been experimentally measured. Negative energy is real. However, the amount of negative energy produced by the Casimir effect is vanishingly tiny, and the amount needed for Alcubierre's warp drive in its original formulation was anything but tiny. The original calculations suggested you would need negative energy equivalent to about 10 billion times the mass energy of the observable universe. Let me say that again. 10 billion observable universes worth of energy, but negative. That is not just impractical, that is absurd. That puts the concept so far beyond any conceivable technology that it might as well be magic. But physicists are creative, and over the years since 1994, many researchers have found ways to dramatically reduce this energy requirement through modifications to the bubble geometry. In 1999, Chris van den Broek published a paper showing that if you made the bubble wall very thin and the bubble interior extremely small on the outside, but warped space to be large on the inside, sort of like a science fiction idea of something being bigger on the inside, you could reduce the energy requirement from that absurd 10 billion universes down to about 3 solar masses worth of negative energy. 3 solar masses is still an extraordinary amount of energy, roughly equivalent to the total energy output of our Sun over billions of years. But it is at least a finite, conceivable amount. It exists in our universe. Then, in 2011, Harold White at NASA's Johnson Space Center proposed that by oscillating the shape of the bubble wall, by making it vibrate at specific frequencies, you could reduce the energy requirement even further. His calculations suggested that you might be able to get the energy requirement down to something equivalent to about 700 kilograms of exotic matter. Now, we still do not know how to create or contain 700 kilograms of exotic matter, but 700 kilograms is a human-scale quantity. It is something we can at least conceptually imagine, as opposed to universe-scale quantities. And in 2021, Eric Lentz at the University of Göttingen published a paper that suggested it might be possible to construct a warp metric that uses only positive energy, no exotic matter at all. His approach used what are called soliton solutions, self-reinforcing wave packets in space-time that maintain their shape. The energy required was still enormous, far beyond our current capabilities, but it was conventional energy. No negative energy density at all. If this holds up to further scrutiny, it could remove the single biggest theoretical objection to warp drives. So the energy problem, while severe, has been steadily shrinking over the decades. What once seemed absolutely impossible now seems merely extraordinarily difficult. And in physics, extraordinarily difficult problems sometimes get solved given enough time and ingenuity. But here is where we need to return to that 2012 Sydney paper. Because even if we solve the energy problem, even if we figure out how to create a stable warp bubble with manageable energy requirements, there is this other problem. This much worse problem. The problem that is not an engineering challenge, but a fundamental physical consequence of how warp bubbles interact with the universe around them. Let us go through the physics of particle accumulation, step by step. Because this is where the horror really begins. Picture the warp bubble moving through interstellar space. Remember, interstellar space contains roughly 1 to 2 hydrogen atoms per cubic centimeter on average. It also contains photons from the cosmic microwave background radiation, roughly 411 photons per cubic centimeter. It contains cosmic ray particles at much lower densities but much higher energies. And it contains trace amounts of dust, helium, and other elements. Now, as the warp bubble moves forward, its front face encounters these particles. What happens? To understand this, you need to think about what the front face of the warp bubble actually is. It is a region where space is being violently contracted. Space-time there is curved in an extreme way. It is not a physical wall made of matter. It is a wall made of curved space-time itself. And when particles encounter this curved space-time, they do not simply pass through it. The extreme curvature captures them. Think of it this way. Gravity is the curvature of space-time. A massive object like the Sun curves space-time around it. And that curvature is what we experience as gravity pulling us toward it. The front face of a warp bubble has extremely high space-time curvature, far more extreme than any planet or star. When a particle encounters this curvature, it gets caught, just as a particle falling toward a black hole gets caught by the extreme curvature near the event horizon. But there is more to it than just capture. The particles do not just get stuck on the bubble wall motionless. They get blue shifted. Blue shifting is what happens when a photon or particle gains energy due to gravitational effects or relative motion. When light climbs out of a gravity well, it gets red shifted, losing energy, and its wavelength stretches toward the red end of the spectrum. The opposite, blue shifting, happens when light falls into a gravity well, gaining energy, and its wavelength compresses toward the blue end. The particles trapped on the front face of the warp bubble are in an extreme gravitational environment, and they get blue shifted to extraordinary energies. How extraordinary? This depends on the speed of the warp bubble. The faster the bubble moves, the more extreme the space-time curvature at its front face, and the more energy the trapped particles gain. For a warp bubble moving at 10 times the speed of light, the blue shifting factor is immense. Particles that were just cold hydrogen atoms, with thermal energies of a fraction of an electron volt, can be blue shifted to energies of millions or billions of electron volts. These are energies comparable to the highest energy cosmic rays we detect. Particles with the energy of a baseball thrown by a professional pitcher concentrated into a single proton. And remember, this accumulation is happening continuously. Every cubic centimeter of space the bubble passes through adds more particles to the growing collection on the front face. Over a trip of 1 light year, the bubble sweeps through a volume of space equal to its cross-sectional area times 1 light year of depth. Even at just 1 or 2 particles per cubic centimeter across a distance of about 9.46 trillion kilometers, that adds up to an astronomical number of captured, blue-shifted particles. The McMonigal team's calculations showed that for any reasonably sized warp bubble traveling any significant interstellar distance, the accumulated energy on the front face would be staggering. But here is where it gets truly terrifying. What happens to all of this accumulated energy when the bubble stops? A warp bubble cannot simply vanish instantaneously. It has to decelerate. The space-time distortion has to smooth out. The contracted space in front has to return to normal. The expanded space behind has to return to normal. As this happens, the extreme curvature of the front face relaxes, and all those particles that were being held in place by that extreme curvature are no longer held in place. They are released. And they are released in the forward direction, not uniformly in all directions. Forward, the geometry of the Alcubierre metric naturally focuses this release into a concentrated beam in the direction of travel. The McMonigal team showed this through their simulations. When the bubble decelerates, the particle release is highly directional, concentrated ahead of the former bubble, exactly where the destination is. The result is a burst of incredibly high energy particles and radiation aimed directly at whatever is in front of the ship. A burst with energy, comparable to a gamma-ray burst, but focused into a much narrower cone. This is not a gentle dissipation. This is a directed energy release of catastrophic proportions. Let me put this into perspective with some comparisons so you can appreciate the scale of destruction we are talking about. A gamma-ray burst is the most energetic event we know of in the universe after the Big Bang itself. When a massive star collapses into a black hole, or two neutron stars merge, the resulting explosion can release more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifetime. And this energy is focused into narrow jets. If a gamma-ray burst occurred within a few thousand light-years of Earth, and one of its jets happened to point at us, it would strip away our ozone layer, expose the surface to lethal ultraviolet radiation, trigger a mass extinction, and potentially sterilize the entire surface of the planet. The energy released by a warp bubble upon deceleration, for a trip of just a few light years at a superluminal velocity of 10 times light speed, would be in this range. It would be a focused beam of ultra-high energy particles with enough energy to strip atmospheres, boil oceans, and sterilize planetary surfaces. And unlike a gamma-ray burst, which lasts only seconds, the release from a warp bubble could potentially last longer, depending on the deceleration profile, bathing the destination in lethal radiation for an extended period. Now think about what this means practically. You build a warp drive. Your destination is an Earth-like planet around another star. You engage the drive, you travel for a few days or weeks, and when you arrive, you release enough energy to kill everything on that planet. The very act of arriving is an act of destruction. You do not need to carry weapons. You do not need to intend harm. The physics of your arrival is the harm, and it gets worse when you consider the scaling. The McMonigal team showed that the amount of energy released scales with both the velocity of the bubble and the distance traveled. Faster bubbles accumulate more energetic particles. Longer trips accumulate more total particles. So the scenarios where warp drive would be most useful, traveling to distant stars at high superluminal speeds, are exactly the scenarios where the destruction would be most severe. A slow warp trip to a nearby star would be somewhat less destructive, but somewhat pointless. A fast trip to a distant star would be exactly what we want, but would release phenomenal amounts of energy at the destination. There is another deeply troubling aspect of this that the researchers pointed out. The focusing effect is not just about the geometry of deceleration. It is actually built into the fundamental mathematics of the Alcubierre metric itself. The metric naturally creates a focal point ahead of the bubble where energy tends to concentrate. This means that even during travel, not just at arrival, there is a concentration of energy at the leading edge of the bubble that points forward. Some of this energy may leak forward during travel, potentially damaging things in the bubble's path long before arrival. Let me also address something that people often ask about at this point. What about the cosmic microwave background radiation? The CMB is not particles in the traditional sense. It is photons, leftover radiation from the early universe that fills all of space with a very faint glow at a temperature of about 2.7 Kelvin. These photons are extremely low energy individually, but there are a lot of them, 411 per cubic centimeter, everywhere in the universe. And when a warp bubble encounters them, they too get blue shifted. The CMB photons that hit the front face of the warp bubble get compressed to much shorter wavelengths and much higher energies. Low-energy microwave photons become high-energy gamma rays. The conversion is proportional to the blue shift factor, which is related to the warp speed. At 10 times the speed of light, microwave photons become hard gamma rays. At higher speeds, they become even more energetic, and there are so many of them, filling every cubic centimeter of space, that their contribution to the destructive burst at arrival is enormous. In fact, the McMonigal team found that for certain trip parameters, the contribution from blue-shifted CMB photons actually dominates over the contribution from interstellar hydrogen. The cosmic microwave background, this gentle whisper of radiation left over from the birth of the universe, becomes a death ray when concentrated and blue shifted by a warp bubble. There is a deep irony here that I want you to appreciate. The cosmic microwave background is often described as the oldest light in the universe. It has been traveling through space for 13.8 billion years, gradually cooling, gradually losing energy, becoming this faint, cold remnant of the hot beginning. It is beautiful. It is harmless. It tells us the story of the universe's birth. And warp travel would take this ancient, harmless light and turn it into a weapon of mass destruction. The universe's own baby photo becomes a death sentence for anything in the path of a decelerating warp bubble. Now, I want to take a moment to address the question you are probably already thinking about. What about the people inside the warp bubble? Are they safe? The answer is surprisingly yes, at least in theory. The interior of the warp bubble is, by design, a flat region of space-time. No curvature, no tidal forces, no acceleration. The crew inside would feel perfectly normal. They would not experience any of the particle accumulation or blue shifting because those effects happen at the bubble wall, which is external to their flat space pocket. However, this safety comes with its own severe problems. The flat interior creates what physicists call a horizon problem. The interior of the bubble is causally disconnected from the exterior. What does this mean in plain language? It means that once the bubble is formed and moving, no signal from inside the bubble can reach the bubble wall, and no signal from outside can reach the interior. The crew cannot communicate with the outside universe during travel. More critically, they cannot send any signal to the bubble wall to tell it to stop, slow down, speed up, or change direction. This is a direct consequence of the faster-than-light nature of the travel. If the bubble is moving faster than light, then any light signals sent from the interior toward the front wall would never catch up to that wall. It would be like trying to catch up to something that is moving away from you faster than you can run. You will never reach it. What this means in practice is that a warp drive trip would have to be entirely pre-programmed before departure. You would need to set the destination, the speed, the deceleration profile, everything, before the bubble forms. Once you are inside and moving, you are a passenger with no control. If something unexpected appears in your path, an asteroid, a rogue planet, another ship, you cannot avoid it. You cannot stop. You cannot steer. You are committed to whatever trajectory was programmed at the start, and you cannot see where you are going. Light from ahead of you cannot enter the bubble in the normal way because the bubble is moving faster than that light can propagate. The exterior universe is invisible to you during transit. You are flying blind at faster than light speed with no ability to change course. This alone would make warp travel extraordinarily dangerous, even without the particle accumulation problem. But combined with the particle accumulation problem, it creates a nightmare scenario. Not only will your arrival destroy your destination, but you cannot even observe your destination during travel to confirm it is still there, or to adjust your arrival point to avoid populated areas. You are a blind, uncontrollable, faster-than-light projectile that will release a lethal burst of radiation upon stopping, and you cannot do anything about it once you are in transit. Let us now go deeper into the physics of why this focusing effect happens, because understanding the mechanism will help us evaluate whether any proposed solutions could work. The Alcubierre metric describes a specific relationship between the space-time curvature and the velocity of the bubble. The key mathematical object is something called the shape function, which describes how the curvature varies from the flat interior through the bubble wall to the flat exterior space. This shape function determines the thickness of the bubble wall and how sharply the transition occurs between warped and unwarped space. At the front face of the bubble, space is being contracted. This means that the spatial distances ahead of the bubble are being reduced. if you imagine coordinate lines drawn through space. At the front face of the bubble, those lines are being squeezed closer together. A particle sitting in space ahead of the bubble sees the bubble approaching, and from the particle's perspective, the space around it begins to distort. The particle gets swept into the high curvature region of the bubble wall. Once in the bubble wall, the particle exists in a region of extreme space-time curvature. The York time, which is the mathematical measure of how space is expanding or contracting at any point, is very large and negative at the front face, indicating violent contraction of space. In this region, the particle's energy as measured by a distant observer increases dramatically. This is the blue shifting effect. Now, you might wonder why the particles cannot escape the bubble wall. Why do they stay trapped? Think of it in terms of geodesics, the paths that particles naturally follow through curved space-time. In flat space, geodesics are straight lines. In curved space, geodesics are curved paths, which is why planets orbit stars. They are following the curved geodesics created by the star's mass. In the extreme curvature of the warp bubble wall, the geodesics are so distorted that particles in that region cannot find a path that leads them away from the wall. They are gravitationally trapped, just as light is trapped inside a black hole's event horizon. The curvature is so extreme that all paths lead to remaining in the wall or moving along the wall, not escaping from it. As the bubble travels, more and more particles join this trapped population. The front face of the bubble becomes an ever-growing collection of ultra-high energy particles and radiation, all traveling with the bubble, all accumulating more energy as the trip continues. Then comes deceleration. When the bubble slows down, the extreme curvature relaxes. The shape function changes. The York time at the front face becomes less extreme, and suddenly, those geodesic paths that were trapping the particles change. New paths open up that lead forward, away from the bubble and toward the destination. The particles, carrying all the energy they accumulated during the trip, stream forward along these newly available geodesic paths. But crucially, they do not stream out uniformly in all directions. The geometry of the relaxing bubble wall creates a natural focusing effect. Think of it like a lens. A converging lens takes light coming from multiple angles and focuses it all to a single point. The geometry of the decelerating warp bubble front face acts similarly, taking the accumulated particles and radiation and focusing them forward into a concentrated beam. The McMonigal team calculated the angular distribution of this release and found that it is tightly focused in the forward direction. Most of the energy ends up in a cone with a relatively small opening angle ahead of the bubble. The exact angle depends on the deceleration profile and the bubble parameters, but in most configurations, it is concentrated enough to deliver devastating energy densities to anything directly ahead. Let me now talk about what this destruction would actually look like if a warp-driven ship arrived at a destination planet. First, consider the timescales. The energy release happens as the bubble decelerates. Depending on the deceleration profile, this might take anywhere from fractions of a second to several seconds. From the planet's perspective, a burst of incredibly high energy radiation appears from the direction of the incoming ship. There is no warning, because the ship was traveling faster than light. No light or signal from the ship could have arrived before the ship itself. The first indication that anything was coming would be the energy burst itself. The radiation would arrive at the speed of light or very close to it. It would consist of ultra-high energy photons, gamma rays at energies far beyond anything normally encountered in nature, as well as highly energetic particles. Mostly protons and electrons blue shifted to extraordinary energies. Upon hitting the planet's atmosphere, this radiation would interact with atmospheric molecules. the gamma rays would deposit their energy in the upper atmosphere through a process called pair production, where a gamma ray converts into an electron and a positron, which then radiate more gamma rays, which produce more pairs, creating a cascade. This cascade would heat the upper atmosphere to extreme temperatures almost instantly. The energy deposited would be far more than the atmosphere could absorb and re-radiate. The atmosphere would begin to ablate, literally being blown off into space by the radiation pressure. For a sufficiently energetic burst, the entire atmosphere could be stripped away in minutes. If the planet had oceans, the radiation penetrating the atmosphere or arriving after atmospheric stripping would begin heating the surface water. For the energy levels we are discussing, this would not merely warm the oceans. It would flash boil them. The surface of the planet would be heated to thousands of degrees. Any life, any structure, any trace of organic chemistry would be completely annihilated. The planet's crust itself might be affected. For the highest energy scenarios, the energy deposited could partially melt the surface, turning the top layers of rock into magma. The planet would glow with the heat of the energy deposited on its surface. All of this would happen before the ship even fully stops. By the time the crew, sitting safely in their flat space bubble, is ready to look out the window at their new home, that home is a burning, atmosphere stripped, ocean boiled, surface melted ruin. They have committed genocide, ecocide, complete sterilization, without ever intending to, and without any way to have prevented it once the trip began. Now I want to address what many people immediately suggest as solutions, because this is where the physics gets even more interesting and, unfortunately, even more pessimistic. The first suggestion people usually make is this: could you just slow down gradually? Instead of decelerating quickly, what if you spread the deceleration over a much longer distance and time? Would that reduce the intensity of the release enough to make it survivable? The McMonigal team addressed this. The answer is that gradual deceleration reduces the peak intensity of the energy release, but does not reduce the total energy released. All those accumulated particles, with all their gained energy, must go somewhere. If you release them over a longer time, you get a lower peak flux, but you get it for a longer duration. It is the difference between being hit by a single massive wave and being hit by a sustained flood. The total energy delivered to anything ahead of you is the same regardless of how you decelerate. Moreover, gradual deceleration for a warp bubble is not straightforward. Because the interior is causally disconnected from the bubble wall, you cannot arbitrarily control the deceleration profile from inside. It must be pre-programmed. And there are mathematical constraints on what deceleration profiles are even possible within the framework of the Alcubierre metric. Some deceleration profiles that might be ideal from a safety perspective may not be achievable physically. Even in the best case, where you spread the deceleration over the maximum possible distance, the total energy released forward would still be lethal to anything in the path. You would be turning a point-blank shotgun blast into a sustained beam weapon. Both kill you, just in different ways. The second suggestion people make is more creative. What if you clear the path before traveling? Send a powerful laser or particle beam ahead of you to sweep away all the interstellar matter along your planned route, creating a tunnel of truly empty space for the warp bubble to travel through. This is imaginative, but it falls apart when you consider the numbers. You would need to clear a corridor of space that is the width of your warp bubble and stretches for light years. Even at the low density of 1 hydrogen atom per cubic centimeter, the total number of atoms in such a corridor is in the range of 10 to the power of 40 or more. That is trillions of trillions of trillions of atoms. You would need to push every single one of them far enough off the path that they would not be captured by the bubble as it passes. Furthermore, you cannot clear photons from the cosmic microwave background. The CMB is not matter you can push away. It is radiation filling all of space uniformly. New CMB photons are constantly streaming through every region of space from all directions. You could not evacuate the CMB from a corridor of space, because the moment you cleared it, more photons would flood in from every direction. And as the McMonigal team showed, the CMB contribution to the destructive burst can be dominant for certain trip parameters. So even if you could somehow clear all the matter, which you cannot practically do, the radiation would still accumulate and still be released upon deceleration. Part 2, the third suggestion, is perhaps the most practical. What if you drop out of warp far away from your destination and coast, in using conventional propulsion for the last stretch? You decelerate your warp bubble in empty interstellar space, far from any planets or stars, release all that accumulated energy harmlessly into the void, and then spend the last portion of your journey traveling at conventional subluminal speeds. This is actually the most viable mitigation strategy proposed to date. And it would work, in the sense that it would protect your specific destination from the energy release. But it has several significant problems. First, harmlessly into the void is not entirely accurate. Space is not completely empty anywhere. The energy released would still interact with whatever diffuse matter and radiation exists in that region. Depending on the energy levels, it could create observable effects, potentially dangerous to anything else that happens to be in that general direction, even at great distances. Second, this defeats much of the purpose of warp drive. If you have to coast for the last light year or more of your journey at subluminal speeds, you are adding years or decades of travel time to your trip. The whole point of a warp drive is to get somewhere quickly. Coasting in at even a significant fraction of light speed for the last light year would take over a year. If you need to coast for several light years to ensure safety, you are adding years or decades. Your faster-than-light trip followed by a years-long coast period is still much better than thousands of years of conventional travel, so it is not worthless. But it significantly reduces the appeal of the technology. Third, and most fundamentally, this does not solve the problem. It just points the gun somewhere else. The energy release still happens. The destruction still occurs. You have just arranged things so that the destruction happens in a place where hopefully nothing lives. But for the matter and photons in that region of space, it is still devastation. And there is a deeper ethical concern here. If warp travel becomes common, if thousands or millions of ships are all decelerating and releasing enormous bursts of energy in various parts of the galaxy, the cumulative effect on the interstellar medium could be significant. You would be pumping enormous amounts of energy into space in focused bursts. Over time, this could alter the character of the interstellar medium in traveled corridors, potentially affecting star formation, molecular cloud chemistry, and other processes that depend on the ambient conditions of interstellar space. Let us now examine another proposed solution that takes a fundamentally different approach. In 2002, Portuguese mathematician José Notario published a paper proposing what he called a zero-expansion warp drive. Unlike the Alcubierre metric, which explicitly contracts space ahead and expands space behind, Notario's metric achieves faster-than-light travel without any expansion or contraction of space at all. Wait, you might say. If there is no contraction of space in front and no expansion behind, how does the ship move? The answer is through a different kind of space-time distortion. Instead of expansion and contraction, Notario's metric uses a pattern of space-time curvature that creates a kind of sliding motion. Imagine a conveyor belt made of space-time itself. The ship sits on the belt and gets carried along without any volume changes in the space ahead or behind. This sounds promising for our problem. If there is no violent contraction of space at the front face, perhaps particles would not get trapped and blue shifted. perhaps the energy accumulation problem would go away. Unfortunately, the McMonigal team and subsequent researchers found that the Notario metric does not completely escape the particle problem. While the mechanism is different, particles still interact with the distorted spacetime of the bubble wall in the Notario metric. The specific details of how they accumulate and what energies they reach are different from the Alcubierre case, but the fundamental issue persists. Any faster-than-light warp metric, whether it uses expansion and contraction or some other form of spacetime distortion, creates extreme curvature at the bubble wall, and extreme curvature traps and energizes particles. The details vary, but the general conclusion remains. This suggests that the particle accumulation and destructive release might be a generic feature of all faster-than-light warp drives, not just Alcubierre's specific version. It might be that any warp metric capable of superluminal travel will necessarily have this problem, because any such metric necessarily involves extreme spacetime curvature somewhere, and that curvature will necessarily interact dangerously with ambient particles and radiation. If this is true, and the evidence strongly suggests it is, then the destruction problem is not a bug that can be fixed with clever engineering. It is a feature of the fundamental physics. It is built into the structure of general relativity itself. Any way you distort spacetime to achieve faster-than-light travel will capture and energize ambient matter, and that energy will be released at your destination. Now let us discuss something even more unsettling: the weapon implication. Imagine for a moment that a civilization develops warp drive technology. They discover the particle accumulation problem. They realize that arriving at a destination releases devastating energy in a focused forward beam. A moral and ethical civilization would see this as a terrible obstacle to peaceful exploration and would work to mitigate it, perhaps by using the coast-in from far-away approach. But what about a less ethical civilization? Or what about a civilization at war? A warp-driven object does not need to carry any weapons to be a weapon. It does not need explosive warheads. It does not need antimatter bombs. It does not need anything at all except the drive itself and a flight path pointing at the target. The simple act of traveling towards something at warp speed and decelerating near it is an attack. The physics provides the destructive energy for free. All the accumulated interstellar medium and cosmic microwave background radiation becomes the weapon's payload. And unlike conventional weapons, there is essentially no defense against this. The warp bubble arrives faster than light. No warning can precede it. You cannot see it coming because it outruns its own light. The first indication of an attack would be the energy release itself, by which point it is far too late to do anything. Furthermore, the destructive potential scales with distance. A longer trip accumulates more particles and more energy. So a warp weapon sent from across the galaxy would be more destructive than one sent from a nearby star system. This is the opposite of conventional weapons, which generally become less effective at greater range. A warp weapon becomes more lethal the further it travels. And you do not even need a ship. You just need to create a warp bubble around any mass and aim it at your target. A warp-driven rock would be just as devastating as a warp-driven starship. The destruction comes from the bubble's interaction with the interstellar medium, not from anything the ship carries. This creates a truly horrifying scenario for any galaxy with multiple warp-capable civilizations. The existence of warp technology is inherently destabilizing. Any civilization with a warp drive possesses, by definition, a faster-than-light planet-destroying weapon that cannot be defended against and cannot be detected before it strikes. The mere existence of this technology creates an existential threat to every other civilization in the galaxy. Some researchers have connected this to the Fermi paradox, the famous question of why we do not see evidence of alien civilizations despite the galaxy being billions of years old and containing hundreds of billions of stars. Perhaps civilizations that develop warp drive either destroy themselves with it accidentally, destroying their own colonies and neighboring systems through routine travel, or they use it as a weapon and destroy each other. Perhaps the galaxy is quiet, not because no one is out there, but because warp-capable civilizations inevitably destroy themselves and their neighbors. A grim possibility. Let me now take us into some additional physics that makes the warp drive problem even more complex. We have discussed the particle accumulation and release, but there are other dangerous aspects of warp travel that compound the problem. First, let us discuss Hawking radiation in the context of warp bubbles. Stephen Hawking showed in 1974 that the extreme curvature near a black hole's event horizon causes the spontaneous creation of particle-antiparticle pairs from the quantum vacuum. One particle escapes to infinity, the other falls into the black hole. The escaping particle carries energy away from the black hole, which is what we call Hawking radiation. The bubble wall of a warp drive has similarities to a black hole's event horizon in terms of its extreme space-time curvature. Several researchers, including Finazzi, Liberati, and Barcelo, have studied the quantum effects at warp bubble walls and found that similar particle creation should occur. The warp bubble would emit Hawking-like radiation from its walls. This radiation would be at extremely high temperatures, potentially comparable to the temperatures at which massive particle physics reactions occur. This Hawking radiation at the bubble wall has several implications. First, it represents an additional source of high-energy particles accumulating on the bubble's surface. Even if you could somehow clear all ambient matter and radiation from the bubble's path, the bubble itself would generate high-energy particles spontaneously from the quantum vacuum. These would also be released upon deceleration. Second, the Hawking radiation directed inward toward the bubble interior could potentially be lethal to the crew. The flat space inside the bubble would be bathed in extreme radiation from the bubble walls themselves. This might make the bubble interior far less hospitable than the simple Alcubierre metric suggests. Third, the energy for this Hawking radiation has to come from somewhere. It comes from the bubble itself, meaning the warp field gradually loses energy over time due to this quantum radiation. This could make the bubble inherently unstable, decaying over time whether you want it to or not. An unstable bubble that spontaneously collapses during travel would release all accumulated particles unpredictably, without any deceleration control at all. Now let us discuss another terrifying possibility: closed timelike curves and causality violations. This might seem like a digression from the destruction problem, but it is actually deeply connected. Einstein's special relativity tells us that the concepts of before and after are not absolute for faster than light travel. Different observers moving at different velocities will disagree about the order of events. For subliminal travel, this disagreement never creates a paradox, because all observers agree on the causal order of events connected by subliminal signals. But for superluminal travel, it is possible to construct scenarios where an event is in its own past, a closed timelike curve. Here is how this works with warp drive. Imagine observer A is stationary relative to some reference frame. They watch a warp-driven ship depart from Earth, travel faster than light, and arrive at a distant star. In A's reference frame, the ship departed before it arrived. Normal causal order. But now consider observer B, who is moving at a significant fraction of light speed relative to A. Due to the relativity of simultaneity, which is a fundamental consequence of special relativity, observer B might calculate that the ship arrived before it departed. In B's reference frame, the ship reached the star before it left Earth. Now, if the ship can make a return trip also at faster than light, it can potentially arrive back at Earth before it originally departed. The ship has traveled into its own past. This is a closed timelike curve, and it creates grandfather paradoxes and logical contradictions. This has been a known problem with warp drives since the concept was proposed. Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics somehow prevent the formation of closed time-like curves. Even if no specific law explicitly forbids them, the exact mechanism of how this protection would work is unknown. Some physicists believe that quantum effects would cause the energy at a would-be chronology-violating boundary to diverge to infinity, destroying the warp bubble before the paradox can occur. If the chronology protection conjecture is correct, then it might be that warp bubbles are fundamentally unstable whenever they would create causal paradoxes. And since superluminal travel in most reference frames leads to paradoxes, this might mean that warp bubbles are unstable essentially always, at least at superluminal speeds. An unstable bubble collapses. A collapsing bubble releases its accumulated energy. And we are back to the destruction problem, now with the additional uncertainty of when and where the collapse occurs. There is yet another deeply concerning possibility connected to warp drives. This one involves the vacuum structure of the universe itself. In quantum field theory, the vacuum, what we think of as empty space, is not actually empty. It is the lowest energy state of the quantum fields that permeate all of reality. But here is a question that physicists have long worried about. Is our vacuum the true lowest energy state, or is it merely a local minimum? Is it possible that there exists a lower energy vacuum state, and our current vacuum is metastable, meaning it could potentially decay to that lower state if given a large enough push? If our vacuum is metastable, a process called false vacuum decay could be triggered by an extreme enough event. In false vacuum decay, a region of space transitions from the current vacuum state to the true, lower energy vacuum state. This transition releases enormous energy and propagates outward at the speed of light. The new vacuum state would have completely different physical constants, different particle masses, different force strengths. Chemistry would not work, atoms might not be stable, life would be impossible. And the bubble of true vacuum would expand forever, consuming everything in the universe. Now, could a warp drive trigger false vacuum decay? We do not know for certain. But a warp bubble creates the most extreme spacetime conditions outside of singularities. The energy densities at the bubble wall are enormous. The quantum vacuum is subjected to extreme stresses. If there exists a trigger threshold for false vacuum decay, a warp drive might be one of the few processes in the current universe energetic enough to reach it. If this possibility is real, then warp drive does not just threaten the destination. It threatens the entire universe. Every time a warp bubble forms, there is some probability, perhaps very small but not zero, of triggering a phase transition that would propagate outward at the speed of light, eventually consuming everything that exists. Every star, every planet, every galaxy, every atom, all destroyed by the transition to a new vacuum state where none of the physics we depend on works anymore. This is speculative, I want to be clear about that. We do not know if our vacuum is metastable. We do not know what conditions would be required to trigger a transition if it is. But the very possibility that warp drive could end not just a planet, not just a civilization, but the entire universe, adds another layer to the argument that the speed of light might exist as a fundamental safety limit on reality. Let me now bring us back from these more speculative concerns to the concrete physics of the particle accumulation problem, and discuss where the research stands as of recent years. In 2021, Alexei Bobrik and Gianni Martira published a paper titled Introducing Physical Warp Drives that attempted to classify all possible warp drive solutions into categories based on their physical properties. They distinguished between subluminal warp drives, which move space around a ship at less than light speed, and superluminal warp drives, which exceed light speed. Their key insight was that subluminal warp drives are much less problematic than superluminal ones. A subluminal warp drive does not create the extreme causal disconnection inside the bubble. It does not necessarily trigger the particle accumulation to the same devastating degree because the curvature at the bubble wall can be much milder. And it does not create closed timelike curves. However, the obvious limitation is that a subluminal warp drive does not get you there faster than light could. It might offer advantages in terms of fuel efficiency or avoiding acceleration forces, but it does not solve the fundamental problem of interstellar distances being vast relative to light speed. Bobrick and Martyrier's work suggests that there might be a fundamental physical boundary between the regimes where warp drives are practical and safe, and the regimes where they are dangerous and possibly impossible. The speed of light might not just be a practical limit, but a genuine physical boundary between warp drives that work safely and warp drives that destroy everything. Eric Lentz's 2021 paper on positive energy warp solutions is also worth revisiting in this context. While Lentz's soliton solutions are exciting because they might not require exotic matter, they do not directly address the particle accumulation problem. Even a warp bubble made entirely of positive energy would still sweep up interstellar medium particles as it moves. The energy source of the bubble is different, but its interaction with ambient matter follows the same physics. The space-time curvature at the bubble wall, which is what captures and energizes particles, exists regardless of whether that curvature was generated by exotic matter or conventional matter. So, where does all of this leave us? Let me summarize the current state of understanding as clearly as I can. The Alcubierre warp drive, and indeed any superluminal warp drive we can currently describe mathematically, has the following properties. It requires either exotic matter with negative energy density or enormous amounts of conventional energy, depending on the specific metric used. It creates a causally disconnected interior, making navigation and control during travel impossible. It accumulates interstellar matter and radiation on its front face during travel, blue shifting these to extreme energies. Upon deceleration, it releases this accumulated energy in a focused forward beam with enough power to sterilize planets at the destination. It may produce Hawking-like radiation at its walls that threatens both the crew inside and adds to the destructive release. It may create closed time-like curves that violate causality or trigger instabilities. And it may, in extreme scenarios, risk triggering false vacuum decay that could end the universe. Every proposed solution to the particle accumulation problem has been shown to be either ineffective, impractical, or merely shifting the problem rather than solving it. Gradual deceleration reduces peak intensity, but not total energy. Path clearing is impossible for radiation and impractical for matter. Coasting in from far away works for the specific destination, but does not eliminate the release. Modified metrics like Notario's zero expansion drive still accumulate particles through different mechanisms. And subluminal warp drives avoid the problem, but also avoid faster than light travel, which defeats the purpose. The conclusion that emerges from decades of research is deeply humbling. The speed of light may not be an arbitrary limit. It may not be an engineering challenge to overcome. It may be a fundamental safety feature of the universe itself. A cosmic guardrail that prevents civilizations from destroying each other and themselves through the simple act of traveling. Think about what the speed of light actually does for the universe. It creates causal isolation between distant regions of space. This isolation means that events far apart cannot influence each other instantly. This means that damage cannot propagate faster than C. It means that civilizations can develop in isolation without being immediately subject to the actions of civilizations far away. It means that even if a catastrophic event occurs somewhere, it takes time to propagate, giving the universe time and space to remain intact elsewhere. Without the speed of light limit, the universe would be a fundamentally different and much more dangerous place. Any event anywhere could instantly affect everywhere. There would be no causal structure. There would be no meaningful concept of past and future. Thermodynamics, which depends on causal ordering, would not work. Life, which depends on thermodynamics, could not exist. The speed of light is not just a speed limit. It is one of the foundational pillars on which the entire structure of reality rests. And the warp drive destruction problem might be the universe's way of enforcing this limit, even when you try to get around it. You can mathematically describe a warp bubble that moves faster than light. General relativity allows it on paper. But when you actually build one and try to use it, the physics conspires to create consequences so devastating that it cannot be used safely. It is as if the universe says, "You found a loophole? Fine, but here's what happens when you try to use it." And what happens is that you become a weapon of mass destruction aimed at your own destination. There is something almost elegant about this if you step back far enough. The universe is not arbitrary in its rules. The speed of light connects to causality, connects to thermodynamics, connects to the possibility of life. And the warp drive problem shows that trying to violate one part of this interconnected web creates consequences that ripple through the other parts. Break the speed limit, and you break causality. Break causality, and you break the orderly progression of events that life depends on. The universe is self-consistent in a deep way, and its limits are not punishments but protections. Let me now take us through one more fascinating aspect of this problem that we have not yet discussed, the question of what happens at the quantum level when a warp bubble interacts with the quantum vacuum itself. The quantum vacuum is not nothing. It is a roiling sea of virtual particle-antiparticle pairs constantly popping into and out of existence. Everywhere in the universe, at every moment, the quantum vacuum is alive with these fluctuations. Normally, a virtual particle and its antiparticle appear together, exist for an incredibly brief time allowed by the Heisenberg uncertainty principle, and then annihilate each other and disappear. No net energy is created or destroyed. It is just quantum noise. But in extreme gravitational environments, these virtual pairs can be torn apart before they annihilate. One particle gets pulled one way, the other gets pulled the other way, and they both become real particles rather than virtual ones. This is essentially how Hawking radiation works at a black hole's event horizon. The extreme curvature tears virtual pairs apart. One falls in, one escapes. At a warp bubble wall, similar effects should occur. The extreme curvature would tear virtual pairs apart, creating real particles from the vacuum itself. But there is a difference between a black hole and a warp bubble. A black hole is stationary. A warp bubble is moving, potentially at superluminal speeds. This means the particle creation is happening at a moving surface, sweeping through space, creating particles from the vacuum everywhere it goes. These vacuum-created particles would also accumulate on the bubble wall, just like the interstellar medium particles. They would also be blue-shifted to high energies, and they would also be released upon deceleration. This means that even in a hypothetically perfect vacuum, with no ambient matter or radiation at all, a warp bubble would still accumulate destructive energy from the quantum vacuum itself. This is perhaps the most damning finding for the future of warp drive as a safe technology. You cannot avoid the quantum vacuum. It is everywhere. It is space. You cannot travel through space without interacting with it. And if any interaction with it at superluminal warp speeds generates dangerous particle accumulation, then there is literally nowhere you can go safely at warp speed. The problem is inescapable, not because space happens to contain matter and radiation, which could theoretically be removed, but because space itself, at the quantum level, generates the problem. Now, let me bring us to what I think is one of the most thought-provoking aspects of this entire discussion. Consider the following question: could the destruction problem actually represent something even deeper than a practical limitation? Could it represent a fundamental theorem about the relationship between faster-than-light travel and the laws of physics themselves? In physics, we have several no-go theorems. These are mathematical proofs that certain things are fundamentally impossible within our physical theories. For example, the no-cloning theorem in quantum mechanics proves that you cannot make a perfect copy of an arbitrary quantum state. The no-communication theorem proves that quantum entanglement cannot be used to transmit information faster than light. Bell's theorem proves that no local hidden variable theory can reproduce all the predictions of quantum mechanics. Is the warp drive destruction problem pointing toward a new, no-go theorem? Something like no superluminal warp metric in general relativity can avoid concentrating sufficient energy at the destination to cause destruction above a certain threshold. If such a theorem were proven, it would mean that the destruction is not an engineering problem to be solved, but a mathematical certainty to be accepted. No one has proven such a theorem yet. But the evidence from multiple independent research groups, studying multiple different warp metrics with multiple different approaches, all finding the same general result: particles accumulate, energy grows, release at destination is devastating, strongly suggests that something like this might be true. The McMonigal team at Sydney found it for the Alcubierre metric. Other researchers have found analogous problems for modified metrics. The quantum vacuum calculations suggest it happens even without ambient matter. Every avenue explored leads to the same conclusion. This pattern, where every attempt to solve a problem runs into the same wall from a different direction, is often the signature of a deep physical principle at work, rather than a merely difficult engineering problem. Let me now discuss one more aspect of the warp drive that adds to the danger, and that connects to some of the most extreme phenomena we observe in the actual universe. Gamma-ray bursts, which I mentioned earlier as a comparison point for the energy released by a decelerating warp bubble, are among the most violent events in the cosmos. They come in two types. Short gamma-ray bursts, lasting less than 2 seconds, are produced by the merger of two neutron stars, or a neutron star and a black hole. Long gamma-ray bursts, lasting from seconds to minutes, are produced by the collapse of massive stars into black holes. The reason I bring this up is not just as an energy comparison. It is because there is a physical analogy in the mechanism. In a gamma-ray burst, matter and energy are focused by the geometry of the collapsing system into narrow jets. These jets punch through the surrounding material and emerge as focused beams of devastating radiation. The geometry of the system creates the focusing. In a decelerating warp bubble, the geometry of the bubble wall during deceleration creates an analogous focusing effect. The accumulated particles and energy are channeled into a forward-directed beam by the changing spacetime geometry. Just as Gerb energy is channeled into jets by the geometry of the collapsing star or merging neutron stars. This analogy suggests something important. The focusing effect in warp drives is not an incidental feature that could be easily eliminated by tweaking the design. It is a consequence of the same general relativistic effects that produce the most violent focused energy phenomena in the natural universe. The mathematics of curved spacetime, when geometries change rapidly, naturally creates focused energy flows. This is how gravitational lensing works, how jets form around black holes, how gravitational waves carry energy, and how warp bubbles would release their accumulated energy. To eliminate the focusing, you would need to eliminate the curved spacetime geometry itself. But the curved spacetime is the warp drive. Without curvature, there is no warp. You cannot have a warp drive without curvature, and you cannot have curvature without focusing effects. The destruction seems to be inherent in the very concept. Now let me take a moment to talk about what all this means for the practical future of space travel and humanity's prospects of reaching the stars. The warp drive destruction problem does not mean we are trapped on Earth forever. It does not mean that interstellar travel is impossible. It means that one particular approach, faster than light travel via spacetime distortion, probably cannot work as safely as science fiction has led us to imagine. But there are other approaches. Subluminal travel, while slow, is not impossible. A ship traveling at 10 or 20% of the speed of light could reach nearby stars within decades. This is within the realm of technologies we can at least conceive of building. Nuclear pulse propulsion, as studied in Project Orion in the 1960s, could potentially achieve 5 to 10% of light speed. Fusion propulsion could potentially do better. Beamed energy propulsion, where giant lasers push a light sail to high speeds, as proposed in the Breakthrough Starshot project, could potentially accelerate small probes to 20% of light speed. These approaches would not get us to distant stars quickly. They would not make the galaxy accessible within a human lifetime. But they could make nearby stars reachable within a single generation, or at most a few generations. For a species that exists for millions of years, as we might if we are careful, even slow interstellar travel could eventually populate the galaxy. One nearby star at a time. There are also more speculative approaches that do not involve warp drives. Wormholes, if they could be created and stabilized, would offer point-to-point connections between distant regions of space without the need to traverse the space in between. But wormholes have their own severe problems, including exotic matter requirements and potential instability. As of now, we do not know if traversable wormholes can exist physically, even though they are allowed by general relativity's equations. Another approach that some futurists discuss is not traveling physically at all, but sending information instead. If you could transmit the complete information content of a human mind, a digital copy, at the speed of light, it would arrive at nearby stars in just a few years. The copy could then be instantiated in a new body at the destination, either biological or synthetic. This raises profound philosophical questions about identity and consciousness, but it sidesteps the physical problems of moving matter across interstellar distances. The point is that humanity is not without options, even if warp drive turns out to be fundamentally unsafe. The stars are not forever out of reach. They are just further away, in practical terms, than we might wish. The universe is telling us that we can explore it, but we must do so at the universe's pace, not at the pace our impatience demands. And perhaps that is okay. Perhaps there is something valuable about a slow expansion into the cosmos. A civilization that takes thousands of years to spread between stars has time to mature, time to develop wisdom alongside its technology, time to learn from mistakes without those mistakes being instantly lethal to everything within light years. A civilization with warp drive could destroy a neighboring system before it even realizes what it has done. A civilization with only subluminal travel has time to think, to plan, to be careful. Let me return now to the fundamental physics one more time, because there is one more aspect of the warp drive destruction problem that I want to explore in depth. This involves the relationship between energy, information, and the structure of space-time. One of the deepest results in modern physics is the connection between entropy, information, and gravity. This connection was first noticed by Jacob Bekenstein in the 1970s, when he showed that black holes have entropy proportional to their surface area. Later, the holographic principle, developed by Gerard Hooft and Leonard Susskind, suggested that the maximum amount of information that can be contained in any region of space is proportional to the surface area of that region, not its volume. This is deeply counterintuitive. You would expect that a bigger volume could hold more information, just as a bigger hard drive can hold more data. But the holographic principle says no. The information capacity of any region is limited by its boundary, and this limit is enforced by gravity. If you try to pack too much information into too small a volume, the region collapses into a black hole, hiding the information behind an event horizon. How does this connect to warp drives? Consider what happens at the front face of a warp bubble during travel. Particles are accumulating there, each carrying enormous energy. Energy is information in a deep physical sense. They are connected through the mathematics of quantum mechanics and thermodynamics. As more and more high-energy particles accumulate in the thin shell of the bubble wall, the energy density in that region grows and grows. At some point, the energy density in the bubble wall region might approach the limits set by the holographic principle. You might be packing more information and energy into that thin shell than physics actually allows. If you cross this threshold, what happens? The bubble wall might collapse into a black hole, or rather, into a structure of extreme curvature that resembles an event horizon. If the front face of a moving warp bubble can collapse into something like a black hole due to accumulated particle energy, this would represent yet another fundamental obstacle to warp travel. Not only does the energy release at arrival destroy the destination, but the accumulation during travel might destroy the bubble itself by triggering gravitational collapse of the bubble wall. This is highly speculative, and to my knowledge, no one has published a rigorous calculation showing exactly at what point this would happen for a realistic warp bubble. But the general principle is well established. Too much energy in too small a space creates gravitational instability. And a warp bubble traveling for long distances at high speeds accumulates precisely the kind of extreme energy densities that might trigger this instability. If the bubble wall collapses during travel, the consequences would be catastrophic and unpredictable. The flat space interior might be destroyed instantly. The accumulated energy might be released in all directions rather than in a focused forward beam. The ship and crew would likely not survive. And the resulting explosion, occurring at an unpredicted point along the flight path, could still devastate anything nearby. This adds yet another layer to the list of warp drive dangers. Not only might arrival destroy the destination, but the trip itself might destroy the ship. The warp drive is dangerous from every angle, to the travelers, to the destination, and potentially to the fabric of space-time itself. Now, I want to take a slightly different approach and discuss something that I think is philosophically fascinating about this entire situation. It relates to the question of why the universe seems to have these limits, and what they tell us about the nature of reality. Throughout the history of physics, we have repeatedly encountered situations where apparent limitations turned out to be fundamental features of reality rather than obstacles to be overcome. The impossibility of perpetual motion machines led to the laws of thermodynamics, which are not limitations but descriptions of how energy works. The impossibility of measuring both position and momentum simultaneously led to the Heisenberg uncertainty principle, which is not a limitation of our instruments but a fundamental feature of quantum reality. The impossibility of reaching absolute zero temperature led to the third law of thermodynamics, which reveals deep connections between entropy and the quantum ground state. In each case, what initially seemed like a frustrating you cannot do that turned out, upon deeper understanding, to be a you cannot do that, because reality works in this more interesting way. The limits were not arbitrary walls, they were windows into deeper truths. The speed of light limit, and the warp drive destruction problem that enforces it even for apparent loopholes, might be another such case. It might be telling us something profound about the necessary conditions for a universe that can contain complexity, information, and life. Consider what is needed for life to exist. You need stable atoms, which require specific values of fundamental constants. You need chemistry, which requires atoms to interact in predictable ways. You need thermodynamics to work in the normal forward direction, which requires a consistent arrow of time. You need information to be processable, which requires causal structure, the ability to distinguish causes from effects. All of these requirements depend on the speed of light being a genuine limit on causal influences. If causes could propagate instantaneously, or faster than light, the causal structure of the universe would break down. Effects could precede their causes. Thermodynamics could run backwards locally. Information processing would become incoherent. The speed of light is not just a speed. It is the guarantee that causes precede effects. It is the backbone of causal structure. It is what makes time meaningful, what makes information processable, what makes life possible. And the warp drive destruction problem shows us that even if you find a mathematical way around the speed limit, the physical consequences bring you right back to the fundamental truth. Superluminal causal influences create destructive paradoxes and devastating energy releases. The universe really, truly, deeply does not want causal information traveling faster than light. And it enforces this preference with devastating force. This is not the universe being mean or arbitrary. This is the universe being consistent. The same general relativity that allows warp metrics to be written down also ensures that using them creates unacceptable physical consequences. It is self-correcting. It is self-consistent. It is beautiful, in a mathematical and physical sense, even as it crushes our dreams of easy faster than light travel. Let me now discuss something practical that connects to current and near-future physics research, because this is not just a theoretical exercise. Real physicists are working on these problems right now. At NASA, the Eagle Works Laboratory, initially led by Harold Sonny White, spent years investigating whether tiny warp-like distortions of spacetime could be detected in laboratory settings. Their approach was to use extremely sensitive interferometers, devices that measure tiny differences in the travel time of light along different paths, to look for any evidence that spacetime geometry had been slightly altered by concentrating energy in specific configurations. In 2021, White's team published a paper claiming to have observed something interesting in their data, a pattern that was consistent with what a nanoscale warp metric might produce. However, this claim was met with significant skepticism from the broader physics community. The effects, if real, were at the extreme edge of detectability, and alternative explanations for the data were proposed. As of my knowledge, this has not been conclusively confirmed or replicated. The broader point is that experimental warp drive research exists, even if it is in extremely early stages. The theoretical problems we have discussed, including the destruction problem, are not currently testable experimentally because we cannot create actual warp bubbles. All of our knowledge about what would happen comes from mathematical modeling and simulation, like the McMonigal team's work. This means there is always some possibility that real physics, at the actual extreme energies and curvatures involved, might behave differently from our model's predictions. Quantum gravity effects, in particular, might change the picture. Our current understanding of warp drives is based on classical general relativity, which describes gravity as the curvature of a smooth space-time manifold. But we know that at extremely small scales, near the Planck length of about 10 to the minus 35 meters, space-time is probably not smooth at all. It might be quantized, discrete, foamy, or something else entirely that we do not yet have a theory to describe. A complete theory of quantum gravity, which is one of the holy grails of modern physics, might change our understanding of warp drives in fundamental ways. It might show that warp bubbles cannot actually form in the first place, making the destruction problem moot. Or it might show that quantum effects somehow tame the particle accumulation, making warp travel safer than classical general relativity predicts. Or it might make things even worse, introducing additional quantum instabilities that make warp bubbles even more dangerous and unstable. We do not know, and we will not know until we have a theory of quantum gravity. String theory, loop quantum gravity, causal set theory, and other approaches are all attempting to provide this, but none has yet been confirmed experimentally. Until one is, our understanding of warp drive physics remains incomplete. However, I want to be careful not to give false hope here. The history of physics shows that when classical theories predict something problematic, quantum theories usually make the problem worse, not better. Classical physics says black holes are bad. Quantum physics says they are worse, adding information paradoxes and Hawking radiation instabilities. Classical physics says the vacuum is simple. Quantum physics says it is complicated, adding virtual particles and vacuum energy problems. So the most likely scenario is that quantum gravity effects would add additional problems to warp drives, not solve existing ones. Let me now bring this discussion towards something that I think ties everything together and provides a satisfying conclusion to our journey today. We started with a dream. The dream of humanity reaching the stars. The dream of a technology that could cross the vast gulfs between solar systems in days or weeks instead of millennia. The dream of a galaxy open to exploration, colonization, adventure. And we have seen that dream confronted by reality. Not the reality of engineering limitations that clever scientists might eventually overcome, but the reality of fundamental physics that seems to say, this particular dream, in this particular form, carries a terrible cost. A cost measured in destroyed planets, sterilized ecosystems, and potentially shattered civilizations.